So now it's time to start talking about different types of circuit elements. We've been talking about the generic element for the last two units, but now it's time to move away from those abstractions and start moving into real circuit elements that you're going to see. And this also allows us to introduce the concept of circuit symbols. So as we've seen in a circuit diagram, we've developed the diagrams in terms of just the generic elements circuit symbol, which is this here. Perhaps there's terminals, perhaps there's a voltage, and they're labeled. This is a generic circuit symbol. And as we said before, circuit diagrams are a graphical language for communicating how electrical energy flows. So each different component, for example a battery or a resistor or a light bulb, all of them have different symbols that we use in this graphical language. In general, we have to learn each one, how they work, and how we can work with them. Today we're going to be focusing only on voltage sources, and in particular, a type of voltage source called an independent voltage source. So, what does the word independent mean? It means the voltage does not depend on anything else. So, things like a battery would be an independent voltage source. Its voltage is, say, 9 volts, whether there's something attached to the circuit or not. That's why we call them independent voltage sources. We typically shorten it to just voltage source when we mean independent voltage source, because these are extremely common, and most circuits have one. Dependent voltage sources are something we'll be getting to in a different video, and they're sources where their voltages does depend on something else in the circuit. So we begin with looking at the circuit symbol. There are multiple circuit symbols for the same type of element, unfortunately. It would be very nice to be able to say this is the circuit symbol for this type of source. However, there are many different reasons that we use the different symbols. Generically, we use this symbol here. This is a independent I voltage V source S. Typically though, we will just call it Vs. Normally, if we're drawing this in an actual circuit, it'll have a known voltage, say 10 volts. So we'll draw it with 10 to imply 10 volts. If we meant 10 millivolts, we'd have to say it. Typically, when it's just in volts, it's assumed. But when you're drawing your currents and your voltage sources and everything else, it's recommended to leave the units in until either you're comfortable or it's unambiguous what you mean. Another one you're going to see, which represents almost the same thing, is a battery symbol. And again, it might have, say, 10 volts across it. This one specifically means battery. Sometimes you'll see it with multiple, and it'll still say 10 volts. What this means is this whole element has 10 volts across it, from this point to that point. Keep in mind, there are a long and a short line for this one. The long one represents positive, or higher voltage. And the short one negative. If you'd like a way to remember which one is which, just remember that the long one is positive and positive is good, so you want more of it. How do these relate to the generic circuit elements that we've been talking about? Well, I'll draw 3 equivalent ways of drawing this element. This is the generic method, the battery, and this both correspond to an element that has 10 volts and a minus and a plus. Now is the time to talk about something called ideal versus reality. And I'm putting this in capital letters because it's important to know that when we talk about circuit elements, we're making certain assumptions. Almost always these assumptions don't matter. However, there are some times we can draw a circuit diagram that's physically impossible. Here's one of the times we can do that. Let's say that I have a voltage source at 10 volts. Could I draw a circuit that does this? Certainly, I just did. But what is this circuit really telling me? The first thing we know is that there's 10 volts across the terminals. However, if you remember, anything connected by a wire must be the same voltage. So anything on the same wire is the same voltage. Here's the problem. What these two things taken together mean is that 10 equals to 0. If this is my reference voltage here, that means this is 0 volts, this is 10 volts, but they're connected by a wire. 10 equals to 0. Not physically possible. Another time that we might have a physically impossible thing is if we have two voltage sources of different voltages connected to each other. Let's say this one is 10 volts and this one is 3 volts. Again, we have a problem. This one, if this is my reference voltage, says this is 0 and this is 3. This one says this is 0 and this is 10. And they're connected via a wire and therefore should be the same voltage. Again, this is not physically possible. Now you might be saying, but hang on a second, I could, in theory, take a 9-volt battery and a 10-volt battery and connect the terminals together. What would happen? This is when we deal with the fact that our ideal voltage sources, as drawn in our circuit, are not the same as a real voltage sources physically we can hold in our hands. Although it's a little bit complex, inside of a battery there are in fact elements that we might draw as circuit elements. These circuit elements are ignored when we're dealing with ideal voltage sources. So rest assured, you can't take a 10-volt battery and 9-volt battery, connect them together and have some cataclysmic problem, although it's not a good idea in general. What the key is that the ideal assumptions that we make, sometimes we might be able to draw circuits that are not physically possible. As long as we follow most of the rules, it's not really going to come up much. So, the next step is to learn about resistors. Resistors are something that we're going to be working with a lot in this course. So, it's a good idea to introduce them now. And in particular, there's something called Ohm's law. A resistor is an element that restricts the flow of current. And one very important thing is they always absorb energy. Now, how do we draw a resistor? Well, the circuit element for a resistor is a scraggly line. There are actually guidelines for how many triangles we should be drawing, but for the most part, as long as there isn't any ambiguity, any number from 2 to 3 is fine. In a resistor, we typically say there's positive and negative. Current always enters the positive, and voltage always goes this way. In other words, due to the passive sign convention, resistors are called passive elements. They absorb energy from current. The voltage and the current through a resistor are not arbitrary. I couldn't, for example, say that my current is 10, my voltage is 5, and my resistance is 1. That's not allowed. But what is resistance? It is the proportionality constant that allows me to relate the current and voltage through a resistor. In fact, the equation for the voltage in a resistor is V equals IR. You may have seen this in previous courses, but if not, you're going to be seeing it a lot in this course. We could solve for the resistance and we can develop now a new unit. Resistance is in volts per amp, which is shortened to ohms, given by the symbol omega. So, for example, I might say that I have a 1 ohm resistor. What does that mean? In order to move 1 amp through a 1 ohm resistor, there must be 1 volt across its terminals. So, let's put this all together and let's ask ourselves the question, in a circuit that contains a voltage source and a resistor, how much current is flowing? So, let's say this is a 10 volt voltage source. And this is a 2 ohm resistor. What is the current? Well, if we take a look at our circuit, I have a positive and a negative voltage across that resistor. You might notice that the voltage source and the resistor are in parallel. How would you have noticed that? The top node of the resistor and the voltage source are connected, and the bottom node are connected. Therefore, they share a voltage and are in parallel. So we can use Ohm's law. By Ohm's law, V equals IR, but we're interested in I. So a little bit of algebra tells us that I is V over R. V, because they are in parallel, is 10 volts. R, as given in the question, is 2 ohms. Therefore, I is equal to 10 over 2, or 5 amps. And that was your introduction to real circuit elements, voltage sources and resistors. These two types of circuit elements are going to become very important in Chapter 2 because it turns out that a lot of the circuit theorems that are true for a general circuit can be developed with a resistor and a voltage source. These are, in a sense, some of the simpler types of circuit elements that we're going to encounter. So, we spend a lot of time studying resistors and voltage sources, and then we generalize all the results to the more complex circuit elements. Thank you.